Hello again, it's Mr. Cunningham, and we're going to be going over forces when they are being pushed or pulled at an angle. And so we will go over just like a general case and how it's going to just kind of like slightly affect your process a little bit, and then we'll go into some actual examples. So just the kind of like broad stroke how we always approach these things is, let's say we have a box, the old physics box, and it is getting pulled by something that is at an angle. And let's just say the angle is theta. So like just any angle, right? Angle theta with the ground. So our process for how we approach this stuff really is not going to change very much. We're always going to draw our free body diagram to take a look at what the forces are doing. So if I'm drawing my forces for everything that's acting on the box here, well, then the free body diagram is going to look like I have this tension force, or let's just call it force, right? We don't know if that's a rope or a handle or whatever, so let's just call it force F coming out. Okay, we also have the ground in contact with the box, and let's just say it's totally still right now. Okay, so for like, we'll just make this a really basic case. So when we draw the free body diagram, we have the force that's going up at an angle. We'll call that force F. We have the normal force here coming up perpendicular out of the ground. It's going up because it's flat ground, right? So it's perpendicular. And then we have a force of gravity that is going down. That is my long range force. And that's all we'll draw in there for now. You know, there could be friction if this thing was moving, or if we knew maybe a little bit more, but like I said, this is just a general kind of case. And we know this is at an angle theta. All right. Now, when I go to set up my Newton's second law equations, my force equations, then I'm going to say, okay, the net force in the x direction is equal to, and I don't know if this thing's constant velocity or anything yet, so we're just going to set it equal to mass times acceleration in the x. And in the y direction, same thing. Net force in the y is equal to mass times acceleration in the y. Okay, now it's pretty safe to assume that this thing is not accelerating in the y. Usually when we deal with something that's sliding on the ground, or not sliding, but it's on the ground, you know, things aren't just shooting up into the sky, or they're not like all of a sudden accelerating down into the ground. So usually we can say the y direction is equal to 0, but we'll just leave it like this for now. When I go to, let's look at the x direction first. When I go to sum all the forces in the x direction, the issue is I don't know, this force F is at an angle, and we don't know how much of this force is in the x direction, right? Right now it's going to the right and up, so it's kind of a mixture of the two. So we want to figure out how much is actually going to the right in the x direction, and to do that we're going to use our old friend SOHCAHTOA. Alright, so we're going to do a little trig. So this is where we use the components that we've been practicing. So I'm going to break this force into its x and y components. So I'm going to draw an arrow going to the right, and that would be its force in the x direction. So we'll call it Fx. Okay, and then going up from there, I have my how much it's going to be in the y direction, and that would be, let's call it Fy. Now I have different colors, so I'm using the different colors. Usually you'll use this as like a dotted line or something to show yourself that it's a component. But and now these are my pieces. Now this green one right here, this is actually showing how much in the x direction it's going. So let's do our force equation in the x direction, right? Well, let me look, right? I only have one force now that is going in the x direction. That's this Fx. So I'm going to say this Fx force is equal to mass times acceleration in the x. Easy enough? Okay, well, I want to know what that x force is. And so this is where we use SOHCAHTOA. And let's do a little scratch work over here on the side, right? That means right now I have a right triangle with F, and then I'm worried about this F in the X direction right now. And to do that, if that is adjacent to my angle, I'm going to be using cosine. Right? So I would, to figure out the magnitude of this X component, I would say F cosine of theta. Okay, so I can replace that over here. F cosine theta is going to be equal to mass times acceleration in the X. So that's good, and that's the only X force that I have. So I am technically as far as I could go in this actual X direction right now. Now, if we look at the Y direction, right, I have a few more forces in the Y direction, so this is going to look a little more intricate. But let me get just a little bit of space. I'm going to move this over here. Okay, and in the Y direction now, I have the normal force that is going up, so I'm going to say normal force. And then plus this Y component, so we're going to say plus, and then we'll use the same color, F in the Y, and then plus, and then my other, so those are the only forces that are going up in the Y direction, and then I have the force of gravity that's going down, and it's, so down means it's going to be negative. And that's all equal to mass times acceleration in the Y. All right. I would be fully set now. The only thing I want to do is I want to figure out, well, what is this Y component? And so again, we're going to use trig, SOHCAHTOA, right? And if I want to find what is this Y component down here, well, this is now opposite of my angle. And so I'm going to use sine, and I'm going to say F sine of theta. So this would be, I would have normal force plus F sine of theta, and then minus whatever the force of gravity is, and that's all going to be equal to my mass times acceleration in the Y. Okay, and like I said, this problem so far, there's no numbers, there's no anything, but this is how I'm going to approach it. Notice the process really hasn't changed at all from the qualitative or the more simple problems from before. The only difference is now we have to use a little trig to figure out how much is going in each direction for that force at an angle. Okay, so let's go ahead and let's take a look at some problems where we do have some numerical values. All right, here we go. A person pulls on a 50 kilo, whoa, what just happened? There we go. A person pulls on a 50 kilogram desk with a 200 Newton force that's acting 30 degrees above the horizontal. So let's go ahead and try to draw this. All right, good. I got my pen still. So we got, here's the ground, right? There's a very well drawn desk. There's our 50 kilogram desk. And then we have this person that is pulling on it. Right? But it's not moving. The desk does not budge. So that right away tells me that it has a constant velocity of 0. So I'm going to put that in the back of my head. And let's find numerical values for all the forces acting on the desk. So let's go ahead and draw our free body diagram for this desk, right? And so anything that is crossing that little dotted line is going to be a contact force. So I know this person's pulling up with some force, and that's at 30 degrees. We'll draw that on here in a second. I know there's a normal force, making sure this desk does not fall through the ground. If the person is pulling it, right, they're trying to pull it to the right and it's not moving, that tells me that there's some friction making sure it doesn't move, and that's going to be parallel to the ground. And from there, that's about all we have, right? So when I go to draw this free body diagram, I have that force, that 200 Newton force, we'll just call it force F. Actually, we can put our our value in for there, right? I know that that is, I'm going to draw it just a little more accurate. All right, that is 200 newtons. And that is at an angle that is 30 degrees with the ground. Okay, and then my other forces that I have a normal force that we don't know what it is yet. I have a force of gravity. And I have a friction force. Remember, our rules for friction is it's always parallel to the surface that it's on. So it's got to be parallel with the ground, right? And that's a friction force. And we want to find the numerical value for all three of these forces that are on here. So we want to figure out what is the force of gravity, what's the force of friction, and what's the normal force in the end. Okay? So I know right away that I have this force that's at an angle. So I want to make my life easier. So let's just break this up into its horizontal. Right there. And its vertical components, right? So in the x direction, we know the hypotenuse. The hypotenuse is 200 newtons. So this x component that is adjacent to my angle, that would be 200 cosine of 30 degrees, right? In this vertical one, it's across from my angle, so I'm going to use sine. So I would have 200 sine of 30 degrees. And then everything else I don't really know yet. Let's see, what else do I know that the desk has a mass of 50 kilograms. So that right there lets me know, okay, I can actually figure out what is the force of gravity. The force of gravity, remember we have our equation. I can always find the force of gravity if I know the mass, because all I need is the mass and I multiply it by the acceleration of gravity, right? So this is going to be 50 kilograms times 9.8, since this problem is most likely taking place on Earth. So that's 490 newtons. Okay, so let's go ahead and now we're going to approach this from Newton's second law. That's how we're going to find all these different forces. All right, so let's do the x direction first. In the x direction, I know there's my Newton's second law in the x direction, right there. Now, what do I know about the x direction? I know that this desk is not moving anywhere. And so that tells me that is a constant velocity of 0. So this has a net force of 0 in the x direction. So we can actually just set this equal to 0. Right? And remember, this is the net x force. So I'm going to net all the forces. I'm going to add them together. So I have 200 cosine of 30 degrees, and then plus negative whatever the force of friction is. And that's all those together need to equal out. They need to cancel out and equal 0. Right? So this is now just going to be a little math. Remember where my calculator is. So let's go ahead and I'm just going to use my phone calculator. So 200 cosine of 30 degrees. Make sure you're doing it in degrees, and that is equal to 173.2. So 173.2 newtons minus whatever the friction force is equal to 0. And so if there's only two forces there, well, the friction force needs to be the exact same amount, just in the opposite direction. So we know the friction force is going to be equal to 173.2 newtons. Okay. In the y direction now, the y direction's got a few more, but it doesn't mean our process changes at all or anything. So I'm going to scoot over just a little bit, make a little bit of room. Let's do this in Let's just make our pen a little skinnier so we can actually fit everything, right? In the y direction, same thing. We know this thing is not flying away. It's not accelerating up or down, so the net force in the y is equal to 0. So I need to now net all my y forces. Well, I have 3 y forces. I got normal force going up. I have this component force also going up, and then I have the force of gravity going down. So I have normal force plus, this is 200 sine of 30 degrees, minus, we said the force of gravity was 490 newtons. So actually, I'll just leave it as force of gravity for now. That equals 0. So now let's plug in everything that we know. We don't know normal force. We do know that 200 sine of 30 is 100 newtons. Again, you easily just plug that into a calculator. And we know that the force of gravity, like we said down here, is 490 newtons. And all of that equals 0. So now it becomes just putting together these numbers and solving for my missing normal force. So if I just add these two, right, we can simplify this. I'd have normal force minus 390 newtons equals 0. And then one last step, I solve for the normal force. That would be 390 newtons. Boom. Right? So we used this force that's at an angle, and we could break it up into its pieces in the x direction and the y direction to figure out what are these pieces, right? What are these missing forces that we're trying to solve for? And that's it. All right? Let's do one more. One more. Here it goes. A man pushes a 2-kilogram broom at a constant speed across the floor. The broom handle makes a 50-degree angle with the floor. So we got, let's try this out. Let's draw it. All right. Broom. There's my broom. Okay, and it makes a 50-degree angle with the floor right there. So that's our angle. And he's pushing on the broom with a 5 Newton force. So he's pushing down on the broom. Okay, we know it's going a constant speed. So right away, constant speed. And I think about Newton's first law. That lets me know that all the net forces are going to cancel each other out and equal 0. So let's draw a free body diagram for this thing now. All right, that force going down, let's see, he pushes with 5 newtons of force. So this is a 5 Newton force, and it is at 50 degrees with the floor. Okay, so that would be like if that was the floor. Okay, we also know the floor is pushing back with a normal force, right? So we got the normal force of the floor resisting. You don't want the broom to go through the floor, right? So the normal force resists that, and it's perpendicular to the ground. We know there's C right here. There's already, like, this is pushing kind of to the right. So we know there needs to be some friction force, making sure that this stays at a constant speed. So there's going to be a friction force resisting that motion. And then the broom has some mass, so we know there's a force of gravity as well. Okay? So this is what my free body diagram looks like. The length of the arrows might be kind of weird, but that's why we're solving for it numerically. So think about the things that we can put on here right now. Right now I know the broom has a mass of 2 kilograms. So I remember that the equation for force of gravity is mass times g, and g on Earth is 9.8. So 2 times 9.8 would give me a force of gravity of 19.6 newtons. And now we just need to figure out, okay, what is the x, this horizontal component right here, and what is this vertical component? And the vertical component's going down now, right? But this is going to be F in the y, and this is going to be that push F in the x. Okay, so remember, I can't use this force that's at an angle. I need to figure out what are the components so I can actually use my Newton's second law equation. So let's do the x direction. We know the net force is equal to 0, right? There's no acceleration happening here or anything. So now I'm just going to add, I'm going to net all of my x direction forces. Well, I have the right here in the x direction, right? And that is adjacent to my 50-degree angle. So we could actually just say, okay, well, if it's adjacent to my 50-degree angle, that means I'm going to have 5 cosine of 50. Let's write that on there. This is 5 cosine of 50. And this is going to be 5 sine of 50 because it's opposite of my angle. All right, so 5 cosine of 50, and in the x direction, I also have this friction force that's resisting it. So I would say plus negative friction force, and that needs to equal 0. So I don't know off the top of my head what 5 cosine of 50 is. So 5 cosine 50, 3.2. So 3.2 newtons minus the friction force. Those two forces netted together need to net 0. So we can solve for the friction force right there and find out that the friction force is also equal to 3.2 newtons. All right, same process now for the y direction. I go and I use Newton's second law. I set up my force equation for the y direction. And I look at the context of the problem. This broom is not accelerating up or down, so I know that the y direction net force is equal to 0. And now I'm just going to add all of my y direction forces. So going up, I have the normal force, so positive normal force, plus then I have going down, right here, 5 sine of 50, so minus 5 sine of 50 minus the force of gravity equals 0. I should have said plus negative force of gravity, and that's all equal to 0. So I'm netting all the forces that are pointing in the y direction, and those should all equal 0. So now I'm going to figure out the math a little bit. So normal force, I don't know what 5 sine of 50 off the top of my head is, so 5 sine of 50, 3.8, so minus 3.8 newtons. This force of gravity we figured out earlier is 19.6, so that would then be minus 19.6 newtons, and all of that needs to be equal to 0. Right? So I can simplify this. I got normal force and 19.6, 3.8 minus 23.4 newtons. So I just combined, these are both negative, so that'd be negative 3.8 minus 19.6. These are both numbers, so I can just combine them to give me 23.4 going down. And now I just solve for my normal force. And I have normal force is equal to 23.4 newtons. So on this force diagram, I know the force of gravity, right? I know how hard the person was pushing. I know the normal force, and I know the force of friction. And all of these forces need to have these values so that the entire net force ends up being 0 and we have this traveling at a constant speed. All right, so we're going to practice this some now in class. Go ahead and check the assignment, and then I will be working with y'all. All right.